Here are quiz 5 solutions for Math 251. I gave you 5 problems, told you to do 4 of them. Really, I did that because I didn't want you to have to do this first one here. But if you did know how to do this one, it's not that hard, and then you could skip one of the harder ones below. But you might not just have not learned this method, then it didn't seem fair to ask you. Anyways, show that the derivative of arcsine of x equals this mess. Here's how you do it. Since we're going to use implicit differentiation, what we want to do is set this up as an equation. So it's y equals arcsine of x. Why is that better than this right here? Well, if I could find y prime, I'd be finding this derivative. But since this is an equation, I can mess with both sides of it. I can take the sine of both sides of the equation and get sine of y equals x. And since I couldn't take the derivative of both sides up here, but I can down here, I'll do that now. The derivative of sine of x would be cosine of x. So the derivative of sine of y using the chain rule would be cosine of y times y prime. And the derivative of x is just 1. So when I solve for y prime, I get 1 over cosine of y, which is kind of an ugly way to leave it, since y is just something we created up here. Y is really just the arcsine of x. So I get 1 over the cosine of the arcsine of x. This is great. This is the right answer. It's just not simplified. It's not this. So what we now got to do is show how this is the same as this. So maybe off to the side, I'm going to simplify. And specifically, I'm going to try to simplify the cosine of the arcsine of x. And the way I'm going to do that is by substitution. I'm going to let t be equal to this arcsine of x, to the inner inverse trig function. And the reason that's useful is now, in this column, instead of the cosine of the arcsine of x, I can just write the cosine of t. And so if I can figure out some information about t, I can figure out what cosine of t is equal to, and I would have my answer. The way I'm going to get information about t is using this statement over here, so kind of two parallel columns. If t is equal to the arcsine of x, then if I take the sine of both sides of the equation, I get the sine of t is equal to x. Or instead of x, I'm going to write it as x over 1. Because if I write it as x over 1, it's easier to see how SOHCAHTOA applies. Draw a right triangle, you put t wherever the hell you want. The sine gives me the ratio of the length of the opposite side to the hypotenuse. That's the SOH in SOHCAHTOA. So opposite is x, hypotenuse is 1. And using Pythagorean theorem, I could figure out this third side. And say this squared plus this squared equals 1. Solve for this, and you'll get the square root of 1 minus x squared. And now that you have this pretty picture, you can figure out the cosine of t. Because t is right here, and cosine is just adjacent over hypotenuse. So the cosine of t is just the square root of 1 minus x squared. And since cosine of t is just cosine of arcsine of x, I go down here, and I say, really, my final answer is 1 divided by, instead of writing cosine of arcsine of x, I'll write what it's equal to. Square root of 1 minus x squared. Maybe that doesn't get a box. Maybe I get like a check, since the answer was given up here. Just wanted to get to that same point. All right, moving on. Using the fact that the derivative of arctangent of x is this, find this derivative. The easiest way to do this is to rewrite the problem. So really what we're trying to figure out is the derivative of something. We don't need that much room. And that something is the arctangent of something else. Well, what else? Well, 1 over 1 plus x squared. Instead of 1 over 1 plus x squared, I'm going to write it as 1 plus x squared to the negative 1 power. And I'm going to color code it the way I have shown here to really emphasize that I have a function in green nested inside a function in red, nested inside a function in blue. When it's written like this, we can figure out the derivative just applying the chain rule a couple of times. Chain rule tells us that to take the derivative of a composite of functions, take the derivative of the outermost function, leaving any inner functions alone. So the derivative of arctangent of x is 1 divided by 1 plus x squared. But I'm not being asked the derivative of arctangent of x. I'm being asked the derivative of a bunch of stuff. So what I'm going to write is 1 over 1 plus a bunch of stuff squared. And that stuff is just 1 plus x squared to the negative 1 power. Now I've taken the derivative of the blue. I'm not done. I still have to take the derivative of the red and the green. So the chain rule tells me to take this and multiply it by the derivative of, well, if it were just x to the negative 1 power, I would say it's negative 1 times x to the negative 2. But it's not just x raised up, this is parenthesis overkill. Well, no, I'm going to leave them in there, just so you can tell that we're multiplying by negative 1 times something. We're not subtracting. Anyways, if it was x to the negative 1, you'd say it's negative 1 x to the negative 2. It's not x to the negative 1. It's something. 1 plus x squared to the negative 1. So instead of negative 1 times x to the negative 2, I'll write negative 1, that's something to the negative 2. Then I'll realize I'm still not done. I have to multiply that by the derivative of 1 plus x squared, which is 2x. I think this right here is a great answer. In fact, I'm going to leave my answer just like that. You could rewrite stuff if you really wanted to. You could call this the negative 2 power. You could put this 2x, make it negative 2x, put it up on top. Put this stuff down on the bottom for the negative 2. Put this up. Lots of different things you can do. I'm going to leave it just like this. Find the derivative. Okay, so this one's kind of tricky. Find the derivative of f of x equals sine of x raised up to the sine of x power. There's a hint here. You can't just use the power rule, right? You can't just say, well, x cubed is 3x squared, so this should be sine of x times sine of x raised up to the sine of x minus 1 power. Yeah, it's not. It doesn't work that way. Power rule only works when you have a variable raised up to a constant. Here I have a variable raised up to a variable, I guess is the way to think about it. So what you want to do is use logarithmic differentiation. What that means is first set this up as an equation, and take the natural log of both sides of the equation. Get this. Haven't done any calculus yet, so now I'm going to take the derivative of both sides of the equation. Well, not quite. I'm going to take the derivative of both sides of the equation at some point. But I just made things a lot uglier, right? We started out here, and now I'm putting in these natural logs. It just makes it uglier looking. Why would you do all that? Well, it's because we couldn't take the derivative with this sine of x up in the exponents. We don't have any rule that deals with an exponent in the base and an exponent in the exponent. I said that wrong. A variable in the base and a variable up in the exponent. We don't have any rules that deal with that. So what we got to do is get this thing out of the exponent. The way you can get it out of the exponent is by applying a log rule. There's a log rule that says that the log of something raised up to an exponent is just that exponent times the log of the base. This is a log rule that I'm going to apply down here. I'm going to take this sine of x, this exponent, bring it down in front, and then multiply that by the natural log of the sine of x. I'm not doing any calculus. I know that feels like the power rule. It's not. This is a log rule. We haven't taken the derivative of both sides yet. Get here. Now I can take the derivative of both sides of the equation. Take the derivative of the left-hand side, the derivative of natural log of y. Well, if it were just natural log of x, it'd be 1 over x. With natural log of y, I'll use the chain rule. It'll be 1 over y times the derivative of that y, which is y prime. On this side, I'll have to use the product rule. Derivative sine of x is cosine of x. Then I'll leave this one alone. And then I'll add to that the derivative of the natural log of sine of x. So this is chain rule. Derivative of the natural log part gives me 1 over sine of x. Then I'm not done. I have to multiply by the derivative of sine of x, which is cosine of x. And I'm still not done because I have to multiply that by this sine of x. All right, this is getting complicated. I should probably label some pieces. This is f prime. This is g. This is g prime. And this is f. I'm making this worse and worse. There you go. Okay, so I almost have my answer. Not quite sure where I'm going to go from here. You can simplify if you want. You can say, oh, I got sine of x on the top and a sine of x on the bottom. Those cancel out. So I got cosine of x times natural log of sine of x plus cosine of x. Fine, if you want to do that. I don't care if you do or you don't. Maybe I'll do that at the end. But what you do have to do is solve for y prime. I got 1 over y times y prime equals all this stuff. So I got to multiply both sides by y. I think just for saving space, 1 over sine of x times sine of x, those cancel out and we just get a cosine of x right here. I only simplified to save space. I don't care if you do or not. And then you're almost done at this stage, except, wait a minute, y? I don't want y's in my answer. There are no y's in my problem. Y is something I created. Y is sine of x raised up to the sine of x power. So replace it. You got sine of x raised up to the sine of x power times the cosine of x. Sorry, there should be an x right here. Times the natural log of the sine of x plus the cosine of x. No way that's going to squeeze. I don't think the printer will print that out, so I'm going to write plus cosine of x down here. Close those parentheses with this one, and call this my answer. Whew. All right, finally, last one. No, not the last one. Number 4, find the derivative of this mess. I think it helps to rewrite this. So we're trying to figure out the derivative of 1 over something. Instead of 1 over something, how about something raised up to the negative 1 power? And what is that something? Well, it's the natural log of something. Natural log of what? Well, it's the natural log of 1 over x. Instead of 1 over x, how about x to the negative 1 power? If you think about it like this, it's a lot easier. You don't have to do it this way. You could do a couple quotient rules if you felt like it. I don't feel like it. So let's take this derivative using the chain rule. On the outermost function, I got stuff raised up to the negative 1 power. So negative 1 times stuff to the negative 2 power. The stuff happened to be the natural log of x to the negative 1 power. Then I'm not done. I've taken the derivative of the blue from the original problem. Now let's take the derivative of the red. The derivative of the red, natural log of something, well, it would be 1 over, the natural log of x is derivative is 1 over x. So the natural log of x to the negative 1 would be 1 over x to the negative 1 times the derivative of x to the negative 1. Derivative of x to the negative 1 is negative 1 x to the negative 2. This right here ends up being the answer. There's definitely easier ways to write this. Maybe I'll write one, although I don't care if you simplify it, so I'll write or. This negative 1 and this negative 1 cancel each other out. X to the negative 1 down on the bottom, I can make that x to the positive 1 by putting it up on top. X to the negative 2 up on top, I can make that x squared by putting it down on the bottom. And then I got the natural log of x to the negative 1 down on the bottom to the negative 2 power. So I'll make it the natural log of x to the negative 1 squared. And I can cancel out one of these x's and one of these x's, and finally get 1 over x times the natural log of x to the negative 1 squared. But really, any of those answers are fine, so I'll put the box around the entire thing, because I don't care if you simplify these. This answer is perfectly good too. It kind of details the steps a little bit better. And if you did things differently, if you use the quotient rule, you might get a completely different answer. It'd just be messy. All right, finally the last one. Find dy dx. Find the derivative of both sides of this equation and then solve for y prime is essentially what this question is asking you to do. Okay, if I'm going to take the derivative of the left-hand side of the equation, I got to use the product rule. Maybe left-hand side. Product rule. We're playing the role of f is x, and I'm playing the role of g is y squared. F prime is easy, that's just 1. G prime is hard. This is a chain rule even if it doesn't look like it. This would be 2y times y prime. What about the right-hand side? Well, for the right-hand side, I got a chain rule. I got a bunch of stuff being squared, but the stuff on the inside here will be a quotient rule. But I think I can get away without writing that. Let's see, the left-hand side, using the product rule, I get f prime, 1, times g, y squared, plus g prime, 2y, y prime, times f. So here's my left-hand side applying this product rule right here. Right-hand side, well, let's use the chain rule, 2 x over y to the 1 power, if you want, times the derivative of x over y. Well, that's going to be quotient rule. I guess I should write it out. With my f is an x and my g is a y. So f prime is 1, but g prime is y prime because y is a function. So if I apply the quotient rule, I got f prime 1 times g y minus g prime y prime times f, which is x, divided by g, which is y squared. Get this mess right here. Okay, now what I gotta do is solve this mess for y prime. Maybe I'll switch colors here. So this gave me that part, and this gave me that part. And so now what I have is y squared plus 2xy y prime. That's just rewriting the order of this thing so it looks prettier to me. Equals, I'm going to take this x over y and distribute it into these two terms. So what I will get is, this is 2x over y, and so the y in the denominator times this y squared right here will give me y to the 3rd power, and then the 2x times the 1y will give me 2xy, and the 2x times the negative y prime times x gives me negative 2x squared y prime. And so now if I could just get rid of this y cubed, then I wouldn't have any fractions to deal with. I'll get rid of it by multiplying both sides of the equation by y cubed. It gives me y to the 5th power, out of room, plus 2xy to the 4th power times y prime is equal to 2xy minus 2x squared y prime. So to get all the y primes on one side of the equation, I'll add this term over here and subtract this term over here. That'll give me 2xy to the 4th y prime plus 2x squared y prime is equal to 2xy minus y to the 5th. So if I factor out a y prime from both sides of the equation and then divide by the stuff that's left over here, I get y prime equals 2xy minus y to the 5th divided by, this isn't going to print very well, what's left on this side after I factor out a y prime, namely 2xy to the 4th plus 2x squared. Could you simplify this? I don't know, probably, maybe. Yeah, maybe not. But regardless, I don't care if you can or you can't, I'm going to leave my answer just like this. But yeah, I don't think this one, I mean, there's always different ways you can write stuff. Simplified is kind of subjective. But as far as like canceling an x or a y from the numerator and the denominator, I don't think you can. So this right here is our derivative, and that is finally the end of this quiz.